So as it turns out, there's time on the space station where many of our crew members, who are also scientists and engineers, can actually conduct their own studies. So we've actually had papers published from the space station from original research done on fluids, for example, by one of our crew members. Well, in this next group, let me preface it by just answering some questions I've been asked, and this is about statistics. So as of May 2017, and not counting the current crew on the International Space Station, approximately 547 people have flown in space from 38 countries. 24 have traveled beyond low Earth orbit, 12 walked on the moon. Of that number, 62% were from the United States, 22% from Russia. Germany, China, and Japan each had 11 persons from their countries fly, so they tie at 2%. France had 10 astronauts, Canada 9, Italy 7, and most of the other countries 1. We've had flyers from Denmark and from Sweden, from countries around the world that have had the opportunity to fly for their nation and to communicate back to them. Many of our flyers, retired flyers, have not stopped their lives once they left NASA. They've stayed in Texas, they've started businesses, they lead institutes, they promote for space exploration, they're entrepreneurs. And so I thought what we'd do is bring 4 of them up in this final session, and they might talk a little bit about their flights, but I'll name them as I introduce them. But I want them to have the opportunity to talk about what they're doing in the space, in the state of Texas in terms of research, commercialization, leadership, and promotion. So with that, I'm going to ask the following individuals to come up, and then when they're seated, I'll introduce each of them. They'll each give a small presentation, and then we'll move into Q&A. So is Dr. Chang here? Franklin? As you walk up, and please take a seat. Dr. Franklin Chang actually was a classmate of mine when we were selected together in 1980, and he has quite a unique background. Franklin, you may sit any place you like. Actually, I'll sit there and you sit next. I take that back. Yeah. So Franklin decided as a very young boy in Costa Rica that he wanted to be an astronaut. So he actually wrote, I think in Spanish, to someone in the American bureaucracy that he wanted to apply to be an astronaut. I believe he got a reply back, but of course didn't speak English at that time. He graduated from high school, immigrated to the United States, and I believe repeated part of his high school year and learned English. He was eventually admitted into the University of Connecticut and got a BS in mechanical engineering. He still was very interested in going to space. And so, confident that after the Apollo program was canceled, that things would ultimately change at NASA, he entered graduate school at MIT in the field of plasma physics and controlled fusion. And his research involved him heavily in the U.S. controlled thermonuclear fusion program, managed then by the U.S. Atomic Energy Commission. I'll let him talk a little bit more about what happened after MIT, but he joined the Charles Draper Labs, eventually was selected as an astronaut, and he's currently chairman and CEO of his own rocket company, the Astra rocket company in Clear Lake City. Greg Johnson. So Greg was selected, well, first of all, he's president and executive director of the Center for the Advancement of Science in Space called CASIS. You heard yesterday about CASIS now helping to populate the International Space Station with research because it is now a federal laboratory. So if you want to get something on board, Greg's the person to talk to. He was selected in 2013 to lead CASIS as its national laboratory. But before that, he was a decorated fighter pilot, test pilot, and as an astronaut. He piloted 2 space shuttle missions, spending 32 days in orbit and contributing to the assembly of the International Space Station. He also had a leadership position at the Glenn Research Center in Cleveland, Ohio for a while. His Bachelor's of Science degree is in Aeronautical Engineering from the Air Force Academy, and his Master's of Science is in Flight Structures Engineering from Columbia University, and he has an MBA from the University of Texas at Austin. The next panelist is Dr. Ellen Ochoa, who was on our planning committee and has been a moderator and a speaker. She hailed early on from California. She is the 11th director of the Johnson Space Center. She joined in 1988 as a research engineer, joined NASA at the Ames Research Center, and then moved to the Johnson Space Center in 1990 when she was selected as an astronaut. I remember interviewing you as in that selection process. She served on the 9-day STS-56 mission, and she flew 3 other flights for a total of 4 flights. She has her bachelor's degree in physics from San Diego State University and a master's degree and a doctorate in electrical engineering from Stanford University. She was a research engineer at Sandia National Labs and the NASA Ames Research Center, and is a co-inventor on 3 patents and has authored several technical awards. She has many awards from NASA, including the Presidential Distinguished Rank. She is a fellow of the American Association for the Advancement of Science and for the American Institute of Astronautics and Aeronautics. She also chairs the Nomination Evaluation Committee for the National Medal of Technology and Innovation. I'd like to introduce now Walt Cunningham. So Mr. Abbey mentioned Apollo 7 and Walt's participation in that. I think what is sometimes forgotten is that there was a long development program before we left Earth orbit, step-by-step engineering development. One piece had to work before the next one fell into place. And Mr. Abbey explained much about that. So this is the 50th anniversary of the beginning of that flight. He graduated from Venice High School in California, joined the U.S. Navy, became and served as a fighter pilot with U.S. Marine Corps. He eventually received his Bachelor of Arts with honors and his Master's of Arts in Physics from the University of California, Los Angeles. And he also spent time at the RAND Corporation. So very privileged to have the 4 of you with me. I think, do I use this mic or do we have another one? And what I'd like to do is, starting with Franklin, and do you have some slides with you? Kate. Oh, I'm sorry. Kate is part of this. Don't go away. I'd already introduced you. Be sure you get up here. Sorry. Okay. So we're going to start with Franklin. Franklin's going to talk about at Astra and hopefully answer one of the questions about how we can get further faster.
Fast. Okay. I don't need I got help here, so. Okay, well, let's get started. These slides are timed, so I got to keep moving quickly. This is a little bit of my family. I come from a family of immigrants from China, USA, Costa Rica, Venezuela. My father's father was a collaborator during the early uprisings in the Chinese Revolution in 1910, and then persecuted when they left and went to Costa Rica. My maternal grandfather joined the Merchant Marine, the U.S. Merchant Marine, and participated in World War I, and then came back to Costa Rica. My mother and my father also immigrated from Costa Rica to Venezuela, and I got my dreams of space in Venezuela. This is the year 1957 when Sputnik made history, and all of us, or maybe many of us, were children of that era and got the space bug, and I was one of those. And I was also impacted by the feat of the USS Nautilus, the first nuclear submarine that was able to dive in the North Pacific and surface again in the North Atlantic, having gone through the underneath the polar cap, the North Polar Cap. My grandfather told me about this, and I was impacted by this and felt that nuclear power would have a very important role to play in the future exploration of space. And so I decided that this was my calling. I wanted to continue to follow space exploration. And in high school, I did my bit with rocket engines. I built quite a few of these rockets. Many of them failed. In fact, most of them failed. Some of them did not fail. This one here was a partial success. It was a 3-stage vehicle that we built for a science fair, launched it from the soccer field in the school, and had a little mouse in the capsule with a little parachute. That mouse did survive. And then I wanted to come to the United States. I had written a letter to Wernher von Braun, who was the guy who wrote, "So you want to be a rocket scientist?" That's what it said. So I said, yes, I wanted to do that. And so I wrote this letter. I got this letter back from NASA. Somebody underlined the second paragraph, last line, saying you have to become a US citizen. And I didn't understand the language at the time, but I got the message. So I decided to emigrate. This is a picture of me, recently arrived in the city of Hartford, Connecticut, where I was able to stay with some distant relatives of mine who got me going. I had come with a one-way ticket to the United States and $50. And so I enrolled myself in a public high school, Hartford Public High School, and repeated my last year of high school. And I was able to learn English enough to get good grades and received a full scholarship to the University of Connecticut. I watched Neil Armstrong and Buzz Aldrin arrive on the moon in 1969, and I felt I was a little closer to what I wanted to do. University of Connecticut, 1973, when I graduated, I had done 4 years of engineering and physics, and I started to get interested in experimental physics. Worked all my 4 years of college in an atomic physics laboratory, learned about all those things. And President Nixon had canceled the Apollo program, so I took a little detour and went into fusion power because I felt nuclear power was an important ingredient to space in the future. I worked in the thermonuclear fusion program at MIT, and then I went to Draper Labs. It was there where NASA issued that call, and on the second try, I was selected, 1980. There's our picture with Bonnie, and also our former administrator, Charlie Bolden. They're in the left down corner. And that's how we started 25 years. I was very, very fortunate to have flown many, many flights. And if there's one thing I learned about space, is it's very difficult, and things can go wrong very quickly. And you have to have redundancy. You have to have a spacecraft that has robustness. So I decided to continue to work on rocket propulsion from the perspective of plasma physics, plasma rockets, enabling a new way of transporting humans fast. Not the traditional chemical propulsion that we have known for many years, but move into a different environment. I did that research alongside with astronaut training for 25 years, and eventually it got very difficult. We built this experiment at MIT for 10 years, operated it, and eventually it was time to move it to the Johnson Space Center. I did that under very difficult conditions at the time because NASA was not really interested, and the Johnson Space Center was not a propulsion center of excellence. But nevertheless, I managed, with the help of Mr. Abbey and several other people, I managed to bring it to Houston. The lab flourished at the Johnson Space Center at the Neutral Buoyancy Laboratory. It was called the Advanced Space Propulsion Laboratory. We spent 10 years there developing the foundations of the Vasimer engine. And we grew the project to a tune of about 50 scientists from most of the national labs in the US, foreign institutions, as well as universities. And eventually, I felt NASA was going a little too slow, and I decided that it was time to move on to the private sector and try my luck in the private sector with the speed and a little bit of money from private investors. And so I went ahead and convinced NASA to give us the IP and founded the Astra Technologies Company, which then became the Astra Rocket Company. And within 2 months of our exit from NASA, we received a very large investment of $6 million, which had been more money in a couple of months than we had received in 25 years of work at NASA. So obviously we took off. The space business for us is implementing space electric power and propulsion solutions for orbiting platforms, supplying electric propulsion systems to other vendors, other spacecraft manufacturers. You know, electric propulsion is something that was not in vogue at the time, but it is now catching on because we now have the ability to develop high-power systems. So this is what we do in space. The company has also installed a small research facility in Costa Rica. And I wanted to just show you before we go, this is the rocket engine firing in our facility here in Houston and Webster. We're about 3 miles or so from the Johnson Space Center. This rocket here is operating at 100 kilowatts, full power. The plasma is 4.5 million degrees. And it gives you the specific impulse, which is 10 times greater than specific impulse of the best chemical rocket that you can build. The challenge for now, for us, for this company, is to fire this rocket for 100 continuous hours. This is a goal that we hope to achieve in the month of September this year. This will be our last activity before we fly. But in Costa Rica, we're delving in the area of transportation, clean energy, and hydrogen, using hydrogen for fuel cell electric vehicles. And we have just finished an ecosystem of hydrogen with electrolysis techniques to generate it using solar and wind. It has been a long process, but at the end of this slide, if you click on that, you'll see the latest activity there. We hope to turn Costa Rica into the first zero carbon country in the world. This was November 27th. This is the first fuel cell electric bus operating in Central America. Only the third one in Latin America, and the only one who is truly totally renewable. We hope to have many more of these transportation vehicles, not just in buses, but also trucks, vehicles, cars, trains, even airplanes. So we're trying to move the country into this carbon-free environment. The day of the inauguration, the president of Costa Rica joined us, along with members of the government and other dignitaries that came to see this activity. This is a combined activity bringing government and private industry. We have several American companies working with us as partners. Air Liquide also from Europe, Cummins, and US Hybrid from the United States. And that completes my presentation. Thank you very much.
Thank you. So if you hold your questions, we'll do it at the end. And Franklin said he had many, many flights. Well, I think he's only one of, 2 people has 7 flights. So he holds the record there. So Greg, would you like to go next?
I better have this. All right, does it still work? Okay, and the slide clicker's right here. So I'm humbled to be up here with this distinguished panel. There's a lot of spaceflight experience, and we take many different segments of this, the 543 people, or 547. I thought it was 531. But anyway, I'll put this right here. So I'm going to take a little bit different tact, I think we all are, for this presentation. I'm going to share with you I'm going to start sort of where I operate right now, managing the ISS National Laboratory. My astronaut career was during the assembly phase of the space station. Right when we arrived in 1998, the first module of the space station went up to low Earth orbit, and during the entire time that I was at the astronaut corps, I was lucky enough to be on just 2 shuttle flights. But the space station was completed right around the time that I had my last shuttle flight. So it's been all about the space station, and so this transition to what I've been doing the last 4 years has been very meaningful to me as we built the space station, and now we're in the utilization era. So I'm going to start off with a video that kind of encapsulates everything that you've been hearing for the last 2 days about research on the space station. And without further ado, let me go with this one. This has sound.
The International Space Station is the most fantastic vehicle ever built.
It's the one-of-a-kind laboratory orbiting about 250 miles above the Earth.
And we perform experiments on the International Space Station.
We can do science, we can do experiments, we can learn how to do things out of this world. And the result will help benefit the people on the ground.
Space station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
The weightless environment will give us insights into things like diabetes and maybe even cancer.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
If we wouldn't have conducted experiments on the ISS, we wouldn't have known that you could use cold atmospheric plasma in such broad application areas we're now exploring.
One of the most promising results has been gained by studying a protein associated with Duchenne muscular dystrophy.
We may be able to slow the disease by half, potentially doubling the lifespan of many of these DMD patients.
We provided eyes-serve imagery for many, many natural disasters, including floods and fires, for deforestations, for volcanic eruptions, and for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
I think it's made people much more aware of the issues of water quality. That's a very powerful thing.
Having the HYCO on the International Space Station has been the ideal test bed for our research.
We can monitor these water bodies from space, and if we can reduce exposures both to humans and even animals, then we've achieved our goal.
And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The space station has done so many things for life on planet Earth. It shows us what human beings can do working together. It shows the science that we can discover.
Over 2,000 experiments have flown on board ISS. 170 countries around the world have participated in some fashion, either in the ISS itself or in one of the experiments. Our rate of research is actually increasing. We're doing more today on board the space station for research than we have ever done before, and that's only going to continue in the future.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
So how can you not be excited about that? So it's been a great privilege to be a part of this amazing project, probably the greatest engineering feat of our civilization. Bonnie told me I had to talk about my space flight, so I included 2 slides, because you all heard about the AMS, the Alpha Magnetic Spectrometer, from Dr. Sam Ting yesterday. It was a very interesting conversation talking about how we're studying our universe to understand about dark matter, dark energy, and naturally occurring antimatter. Well, our last shuttle flight, we had the opportunity to bring the AMS up to the space station, and just like Kate said earlier, don't screw this up. So the AMS went up, and you heard Spanky's voice, Mike Fink's voice on the video, but he was the one that turned on the switch, and the AMS worked just as planned. But the AMS story is interesting. It's sort of a parallel to the space station, the space station program occurring through bipartisan political relationships. K.B. Bailey Hutchinson, she founded this organization. She also was very instrumental in getting the space station program approved, as well as getting the AMS, an additional shuttle flight, to be added to the manifest to put the AMS on board. I included this grainy photo because it has Mark Kelly, who was our commander of STS-134, and since he left, he's been control for the twin study with his brother Scott, who had a year in space. And so you've heard about all these different things, the excitement of what we're doing on the International Space Station, and it was truly wonderful to fly with Mark and to go through with our crew the challenges prior to flight, but then the excitement of getting the AMS and working. I'll close with the AMS story. I just learned a couple months ago that the AMS data that's being collected to do all these different things is now being delivered over to the Human Research Program so they can better understand the real high fidelity understanding of the radiation that's been collecting. So not only is the AMS going to learn all these different things about particle physics, it's also going to contribute to our risk mitigation to get to Mars someday. So I do need to talk a little bit about what I'm doing now. The CASIS has been mentioned a few times, the Center for the Advancement of Science and Space. And about 4.5 years ago, Kate and I were office mates, and this opportunity came up to manage the national lab outside of NASA in a very disruptive way to the way that NASA's done business in the past. The mission was to build a commercial market in low Earth orbit, to invite innovative, non-traditional users to have access to the space station, not just in line with what NASA's trying to do, but what the country's trying to do. And so it's been a great challenge. Our goals are very similar to NASA's. We want to accelerate leadership in space. How can we use the space station to ensure that we are leaders in space technology and space exploration? In the middle, Kate Rubins looked at that photo right there. I think that's the first beating heart cells in space, right? You saw that too. You did a lot up there. But of course, it's pursuing groundbreaking science. And then finally, everything that we do on the space station has to be, has an education story, whether it's for kindergarten, high school, postgraduate, or even lifetime learners. And so the space station STEM mission is critical to the workforce development of our next generation of scientists, explorers, and engineers. So this past year, we've seen great growth in the ISS National Lab community, a community of commercial companies, of nonprofit institutions, universities, and then other government agencies as well as NASA. We're now seeing growing demand. We're seeing institutions put skin in the game. We are now seeing other government agencies have tens of millions of dollars invested in sponsored programs for chips in space and others. NIH and NSF have been leading the way. This past year, we had Target launched a $1 million Cotton Sustainability Challenge, which is very exciting. It's just kicked off. Michael J. Fox set up a Parkinson's project to understand the LRRK2 protein. So many projects went up to the space station last year. It was a banner year. I want to close with one really cool experiment that has been mentioned in this conference, and so I wanted to show it to you firsthand from the Made in Space people who were doing the Z-Bland project, a high fidelity optical fiber, and they're very excited about what they're doing.
There's a really interesting question that we asked ourselves since we started Made in Space, which is, might there be something that you can make only in space that you could bring back to Earth and sell?
So we've built a pilot manufacturing facility that will take Z-band glass up into the International Space Station and then robotically and autonomously pull that glass into optical fiber.
The ideal fiber optic cable is one where the outer diameter does not change at all. There's no impurities inside of it, there's no crystals inside of it, and it's all the same material.
If you make Z-band glass fiber in microgravity, it is somewhere on the order of 10 to 100 times lower attenuation than today's traditional silica fiber.
We hope that we'll be offering, products that are manufactured in space within the next year or two. We would not be here today without NASA and without CASIS and without the investment and opening up of the International Space Station.
So with that, I'll close by saying there's not just one Z-band fiber project headed to the space station, but there are multiple investigators. And so one of the big things we're doing is promoting competition so that we can have the biggest and the best ideas that are building this new space economy. So with that, I'll finish and turn it over to the next speaker. Thank you.
So, Dr. Ellen Ochoa.
I'm here today to talk to maybe a little bit more personally about my story. So I was in my first year of graduate school at Stanford when the space shuttle flew for the first time. And so that was a hugely important event because it was such a different vehicle than had flown before, accommodated many more people, and had this promise of doing all different kinds of research and development in space. And so I was on my way to becoming a research engineer. And a couple years later, we were actually doing science in space. Also, the first woman in space, Sally Ride, flew, and of course she had come from Stanford. And I think that was really the first time it occurred to me that maybe this was something I could actually do. And with my background in research and interest in space, that's really when I became interested in applying for the program. So I got my Ph.D., particularly it was in electrical engineering, optical information processing. Sent in my application to NASA, but figured I'd actually never hear from them again. And I took a research engineering job at Sandia National Labs in Livermore. I worked there for 3 years. I was actually called to come interview at Johnson Space Center during that time. And I wasn't selected, but it certainly fueled the idea that I wanted to work for NASA. And so I ended up moving to a job at NASA Ames Research Center, where I was still working in information processing and leading a research group there, but also getting the chance to learn more about NASA. And a couple years later, I was interviewed again for the astronaut program and selected in 1990. So let me talk a little bit about my first 2 flights. They were kind of just what I had thought about, several years before, of the ability to be able to do science in space. And they were both part of a program that NASA had called Mission to Planet Earth, and we were studying the Earth's atmosphere, and particularly the problem of ozone depletion and the ozone hole. So we had a number of experiments out in the payload bay that were looking at various constituents in the atmosphere and how ozone, and of course this is the upper layer of ozone, is both created and destroyed. And then we were also measuring the amount of radiation that comes from the sun and the spectrum what they were really trying to figure out is, how do you separate out the effects of the changing sun cycle over a 12-year period, 11-year period, from human effects on the atmosphere. So that's a photo of my first crew there on that particular mission. And this is a view, as you look out from the shuttle, look out the aft flight deck into the payload bay, showing that suite of instruments that we were using. And so it was an exciting mission to be on, and a year and a half later, I got to fly again on another mission with these same instruments. And the idea is we were going to fly every year during the 11-year solar cycle. Unfortunately, like so many things at NASA, there were only 3 total flights of these instruments before that program was canceled. But what we were able to do is, because there were a number of robotic satellites that were flying at the time that had in some cases, similar instruments to what we were flying. And of course, these instruments degrade in flight. Primarily, the optics degrade from the UV radiation. And so by sending up the shuttle periodically, we were essentially able to recalibrate those instruments, which made the data that came down continuously from them much more accurate. And so that was one of the big effects of flying this. Also on both of these flights, we had small payloads that we deployed into space and let them go off and fly for a few days, and then we would retrieve them and bring them back home. So it was a way to do another experiment. And I operated the robot arm for those missions. This is one of those payloads that was studying weather in the upper atmosphere, and we had another one that was studying the solar wind. We also do education experiments, and on my first flight, I'm a flutist, and I got to take up my flute. We were filming an educational video for kindergartners through second graders, and it was really about trying to compare living on the ground to living in space and working on the ground to working in space. And we managed to work this into the script as, hey, if you have time in your off hours, this is what you get to do. Although I think you can all attest that there's very little time in your off hours, especially on a shuttle mission. So after I came back from those two flights, it was about 1995 at that point, and we had started to develop the plans for the International Space Station program, which grew out of an earlier US-only station called Space Station Freedom. And so my job in the office was actually to lead the astronaut office support to the ISS program. And at that point, really no hardware had been developed yet. And so we were in the process of supporting a lot of the boards and panels as the hardware started to be developed, as we were refining the requirements for what we needed, and then also to negotiate with members of the Russian Space Agency on how we were actually going to train for and operate the station. So I remember just thinking, you know, really nothing I ever did in graduate school prepared me to go over to Russia, you know, as a 30-something woman, negotiating with these members of the Russian Space Agency who were all 60-something-year-old men and had worked, you know, on their space program since the 1960s. And they had a very different idea of what the space station, how we were actually going to operate. They kind of had this idea of, well, the Russian side's over here, the American side's over here, you both stay on your same sides. You have kind of a checkpoint Charlie in the middle, and if you ever have to like go across, you have to sign in and out. I don't know if you're going to have to show your passport or whatever. You know, we used to say they want to live next door, we want to get married, and so we ended up evolving to a model which was much more collaborative, which was absolutely very important in the early days of the program when you only had 3 people on board. You really could not separate. You needed really all of the people on board understanding and being able to operate all of the equipment, whether it was on the US side or the Russian side. But anyway, got to be involved in negotiating a lot of those agreements. And then I got to fly on 2 flights that were part of the assembly of the International Space Station. So what you're seeing here on the left is what the station looked like the first time I was there. So there had only been 2 previous flights. An unmanned flight on the Russian side to send up the first element, and then the very first US element was brought up by the first space shuttle mission. I was on the second, so we were actually the first one to dock. Of course, there was no people living on board because there was no habitation module at that point. But our job was to bring up a number of supplies, both to transfer to the inside of the station as well as some supplies to transfer on the outside during a spacewalk. And then 3 years later, I got to go back to the station, and so that middle picture is what the station looked like actually when we left. So what we did was bring up the very first piece of the truss structure, you know, the structure that's now about 350 feet long, and the solar arrays hang off of it. We brought up the very first piece, which was about 40 foot long, and attached it to the station during our flight. And I had a series of 4 spacewalks. And I was able to use the station robot arm on that to support all of that. And then, of course, what you see on the right is what the station looks like today. Just, you know, absolutely, I think back to when I first started working station, late 94, early 95, and you had this vision of what you wanted it to be and what you wanted it to do. And I think it's just vastly exceeded everything we were thinking about at that time. So just brought a few more photos. This is a photo of my crew on that first mission that I was at, the one that was the first to dock with the station. We considered ourselves a construction crew, so we brought up the signs to prove it. And that's taken from the node, again, the first US piece that went up. We had 3 women on that flight, so one of the things we brought up was a flag of the National Women's Party that was used in the early 20th century as women were fighting for the right to vote in this country. And really, without that key thing, we wouldn't have women astronauts at this point or in many other fields. A view of me looking out the window, which of course is the most amazing thing I think you can do on any space shuttle or space station mission. That's from the space station. After my 3rd mission, the first one to the ISS, just a picture of me arriving home. I had a year-old son at that point. When I was about to do my last mission, that was about 2.5 years later, had a 3.5-year-old, and my younger son turned 2 while I was in orbit, so I got to do a little video sort of teleconference with him. He wasn't really talking at that point, or at least not in any way that anybody could understand, but we did have a bag of goldfish crackers up there, so I just put a bunch of them, and they started floating around in space in front of me, and he thought that was the funniest thing he'd ever seen, so he enjoyed doing that. And so just a little bit what happened after that, pretty soon, within about a year after that flight, I was asked to join management of the astronaut office and our aircraft ops division. So a directorate, an organization at Johnson Space Center called Flight Crew Operations, and I became the deputy director. 1 month later is when we lost Columbia. So obviously, you know, the first few years I was there, it was really going through the whole recovery, reconstruction, and return to flight effort. And then we got back into the assembly of the International Space Station. And then I became director of Flight Crew Operations, and then shortly after, deputy center director of Johnson Space Center. And then for the last 5 years, I've had the opportunity to be the director of Johnson Space Center. So, of course, we had really finished assembling the International Space Station before I became director. So really, what we've been focused on in the last few years is not only what are we doing, but how are we doing it, and who are our partners? And I think one of the things that we've really expanded over the years is who do we partner with, and in what way do we partner? So we have many more types of partnerships with commercial entities, and in ways that have really evolved from what we used to do, which were always pretty standard contracts. And now we have milestone-based contracts, we have Space Act agreements, and of course we have contracts where we buy services rather than NASA being the one that is developing all the vehicles that we're using in space. And then we've had a lot of efforts at Johnson Space Center where we've tried to change the processes of what we're doing. And so, for example, Kate talked a little bit about the DNA sequencer that we sent up, and again, that was part of an effort that we had where we said, look, we've got to get away from this idea of, you know, everything that we send up absolutely has to work the first time, because that just puts too much process, too much time and energy. And if you're talking about payloads and the fact that we now have vehicles that go up pretty frequently, we can afford to have them not all work exactly like we think the first time, because in the end it will be less expensive if we can put less process in. And so that was an example of sending something up in that mode. Anyway, it's been a huge privilege for me to be able to be the director for the last 5 years. Thank you very much.
So, Walt.
Thank you. My mic on? I have to tell you, the last 45 minutes made me realize just how different my presentation is today. Maybe I'm a slow learner. But first, I would like to thank George for all the nice things he had to say about Apollo 7. It's interesting in today's broad generation out there, most of the people have never even heard of Apollo 7 or Apollo 9. It's because we tested the command module and the lunar module in Earth orbit. Never went to the moon. So people don't even hardly think about that. So actually, you could have referred to me as an ancient astronaut. And so I'm going to be giving some of my personal opinions in the next couple of minutes. And I know some of you may not agree, and so it leads to some questions about that. Because I'm going to talk a little bit about the past, present, and the future. And I can tell you this, that many of us would not have made it today when you take a look at the astronaut crews and what all they've been doing. There's been a difference in, a lot of difference in backgrounds, in education levels, qualifications. They've changed. And why have they changed? Well, because our space program has changed. International relations have changed. Scientific capability has changed today. The age of the flight crews, they've changed. Funding level today has changed. That's just a few of the things that's been changing. So on our panel that you look and you can see here today, I'd like to see the hands in just a minute of a couple of things. One, those of you who are scientists or think of yourself as scientists, can I see your hands, please? Okay. No surprise. How about those with doctorates, Ph.D.s? See the hands? Okay. How about the hands of those who were military fighter pilots?
Thank you, Walt.
Well, I have to tell you, it's easy to tell the other difference here. You know, male and female. It's 3-3 up here right now, so we're doing okay there. But I have to tell you, back in my day, we were all military fighter pilots, and I think the only PhD we had in our first group, 3 groups of people, was Buzz Aldrin's PhD. Right, Buzz? So I'll talk a little bit about past, present, and the future. 500 years ago, the next frontier was the New World. And back in 1519, Ferdinand Magellan set sail on one of the most famous voyages of exploration in history. And that was the first voyage around the world. Well, by the 1960s, the next frontier was space. That's the space out there above our own planet here. And as the exploration of the New World was inevitable 500 years ago, so too is our exploration of space. In 1960, we were working on exploring that frontier. Our crew was intimately involved in the design, the development, and the testing of the command module and the lunar module systems. Actually, we were setting out at that time to beat the Russians. And we did. As you know, first man in orbit was Yuri Gagarin, Russian. That was in 1961. About 9 months later, we finally got our first person in orbit. That was John Glenn. Better mission, of course, than Yuri had. He orbited the Earth. And 3.5 years after that, we had completed the Mercury program and the Gemini program. And during that time, we had demonstrated rendezvous, docking, extravehicular activity. We had passed up the Russians, and in my opinion, the Russians, to this day, have never caught up technically. Apollo 7, well, that was the first of 5 giant steps in an orderly plan to land a man on the moon. And everyone on our team at that time understood that plan. I think George did a pretty good explanation of those 5 giant steps, actually. When Apollo 11 touched down with 17 seconds of fuel remaining, well, those of us remaining, we all started breathing again. And Neil Armstrong, he stepped off into history. He and Buzz were the first 2 people to walk on the moon. I believe today the entire world takes pride in man's greatest adventure. The 60s and the 70s were what I call the golden age of manned spaceflight. Today, the shuttle, I think, in my personal opinion, was the greatest flying machine ever built by man. The International Space Station, that's the greatest space station ever placed in orbit. Also, it's probably the most expensive thing that we've ever put up there. I think what the figures now might be up to about might be as high as $150 billion. We have 5 partners on that station, but we here in America, we pay more than 2/3, and we're totally dependent on the Russians and have been for a number of years. I believe that setting goals and staying on course is essential. Unfortunately, our society today seems risk-averse. NASA is somewhat more bureaucratic and a little less efficient than it once was. And our space program today is beginning to reflect today's risk-averse society. Well, exploration is not about eliminating risk. Exploration is about managing risk. And we fail today not because of an inability to do something. We are failing because of an unwillingness to tackle things in the first place. As the exploration of the New World was inevitable 500 years ago, so too is our exploration of space. Opening up our next frontier requires 3 things: the resources, the technology, and the will to do it. It will also take a long-term commitment. Before we get to Mars, we need to solve many things. For example, interplanetary radiation threat that's sitting out there. Developing a propulsion system, as we talked about, for faster travel, something that could shorten the trip. And I personally believe that we should be focused on developing a habitat on the moon in order to learn how to survive on Mars. All of these things really could take decades. But we're fortunate, actually. Today's unmanned exploration of Mars, I think, has been truly outstanding. And I can also tell you that safety can never be guaranteed when you're exploring the unknown. To venture out into the unexplored frontiers, it has always been necessary that the explorers be willing to die for their efforts. Otherwise, it simply cannot happen. Remember Magellan, when he set out from Spain to explore the globe? He left with 5 ships and 270 sailors. When they returned 3 years later, only one of those original ships was still there. There was no Magellan. He'd been killed. And only 18 of the original sailors were still alive. Well, personally, I feel fortunate to have lived when I did. And I hope that some of you out there can say that same thing after we have landed on Mars. Thank you very much.
Well, thank you. I'd like to open it up to questions now for any member of the panel. Yes.
Last year, the last astronaut class was selected. I was wondering, when might NASA expect to open up applications again for astronauts?
I think that's Ellen.
Yeah, it's on. So what we do is every year we kind of look at what is the flight manifest out there, and what do the missions look like, how many people are going to be flying. We look out 10 or more years. And then we look at the size of our current astronaut corps, how it's changed over the last year, and we sort of do projections about when we think the next class is. So we'll be going through that process in the next few months and looking at it. you know, we've often tried to say, hey, we should probably bring in a few people a little bit more often, you know, rather than waiting 4 or 5 years between classes. But there's a certain amount of just bunch of infrastructure sort of around with selecting and then going through the initial training of astronauts, so it just tends to be a lot more efficient to kind of bring them in as a group. So I don't know, you know, if as you look back over the last few years, it was like 4 years, 4 years, and 5 years between the classes. And so it's probably about that, but you always have to kind of redo it every year to say, what do we know about missions going out at least the next 10 years, and how have those changed, you know, in terms of any of the budgeting process or so.
Any other questions? Yep.
Hi, I appreciate all the work you all have done to progress the opportunities for women to be involved in exploring space. And I'm a little bit concerned that there's not some attention being paid to women participating in the long-duration missions that will go to the moon and Mars. We still haven't had a woman on the moon, and I've speculated about who that might be. Currently, the Russians don't have any women in their cosmonaut corps, and the Japanese don't have any current women in their corps. And so it kind of falls to the Americans and Europeans to provide the data base for the women that are going up in space, and currently there are no women on the space station. And I think that this is going to be a difficult problem to solve, but I was disappointed when the last selection had 5 women and 7 men. I was hoping it would be the other way, that we would have more women and fewer men to try to make up the difference of the reduced number of women that we have already in the astronaut corps, since the Russians are taking up 3 of the 6 slots up there. So I'm wondering if maybe some attention is being paid to the new commercial crew. Will those vehicles accommodate more women visiting space? And we could maybe increase our data pool that way, and perhaps women would not be excluded from the future spacewalks and things, because we'll get more robots involved in the heavy lifting. Maybe the new suit designs will accommodate shorter people, because the women, currently the height restraint for astronaut selection is the minimum has been going up, and this is excluding more women because women are shorter than men. And I'd hate for all these girls we've been encouraging to work hard, do their math and science, get their degrees, and then find out they can't fly because they're too short.
Ellen? Yeah, sure. I'll take that. So actually, I've been really pleased with our last couple of astronaut selections, because in 2013, we had 4 out of 8 who were women, and you know, last year we had 5 out of 7, which is just about 50-50. And when you are selecting from a pool of people who have degrees in science and technology, it's of course nowhere near 50-50 in women yet. So I think in our selections we've way outdone in terms of what we get in the applicants. But we have you know, absolutely outstanding applicants, both men and women, and we're able to find wonderful people of both genders to bring into those classes. And they've also been joined, you know, this latest class has been joined by 2 Canadian astronauts, 1 man and 1 woman. So I think we're doing lots better, and kind of getting the ratio in the office closer to what we'd like to see. But women are certainly participating. Of course, Peggy was, we don't have any women up there now, but Peggy was basically up there all of last year, and you know, has more time in space than, you know, any astronaut, man or woman. So we've made a lot of strides, but we're absolutely committed to continuing to make strides.
Well, I'll take a chance at getting hit on the head here.
You know, Kate's on that side, I'm on this side.
I know. I'm one of those that thinks that whatever job is facing you, you get the best that you possibly can to do that job. I object to having so much of politics and criteria going into so many of these things. And I have to tell you, if the women are the best one to do the job, then they ought to get it. And we can't gripe and complain about it. But today, politics is entering too much of that, And I can tell when I hear somebody talking whether they've allowed that to be the controlling feature for them. So don't hit me, gang.
And I will make a comment about spacesuits. As you probably know, the sizes have been driven more by the Office of Management and Budget than NASA. I have some personal experience in that. So that's why we have started the Aerospace Human Systems Lab at Texas A&M. It's about building next generation suits and going back to custom-made suits like we had during Apollo, where every crew member had 3 suits, like your prime and 2 backups. So we're working to the future on that. Any other questions?
Yes.
Oh, yes.
Well, first of all, as a former president of TAMIST, I want to congratulate you on this wonderful program, and this has been very exciting for me. I did have a question regarding the Made in Space program and the fiber optics. How do we get all these things back if we start making products in space? What is the programmatic approach to getting all of these products back to the planet Earth?
Okay, so actually, when you finished your question, it became more of an Ellen Ochoa question. but I would just say that transportation in general, it's NASA's responsibility to provide for the transportation, and we're on an upswing. We have so many different vehicles and possibilities to get to and from the space station, and it'll even be better in about a year or 2. And then when CRS-2 comes up, we're going to have the Dream Chaser, which is another way to get stuff back. So from a commercial perspective, if some of these really difficult projects bear fruit and you can build a business around them, then there will probably be more and more ways to get back, maybe individual terrestrial return vehicles or something that would bring stuff back as needed. And then I'll leave it to Ellen for the NASA side of that.
Well, I could tell you, the main vehicle we have coming back now is a Dragon vehicle, and actually there's going to be one landing tomorrow, bringing back samples, including, I think, the fiber optic samples that we just recently set up. But since Kate hasn't had another chance to talk yet, she's actually, I think, had personal experience with these cargo vehicles, and particularly I mentioned SpaceX Dragon because it is the one that lands, intact, being able to bring back samples. So maybe you have a comment on that.
Yeah, we have a lot of cargo traffic coming and going from the space station. That actually ends up being one of the critical parts of the job. So, we heard a lot about robotic trading, and we've got that still incorporated in space station. That's how we actually capture these vehicles. So we do free flyer rendezvous, and then space station goes essentially into uncontrolled, non-motion controlled, and free drift, and then we robotically capture the vehicle. So we launched, and within, I think, 72 hours, we had SpaceX 9 Dragon docking, and that's an incredibly busy time frame because that's bringing up a lot of experiments. It's a lot of research that needs to get started. It also then has cold stowage capability, and it's got live animal return now, and so during the dock time frame, you're doing a lot, and then we have this capability to bring samples back down to Earth, and so you're then spending a lot of time getting everything ready and packing this vehicle and bringing home all of the science that we've done on board. So it's an incredible time frame. We also like it an awful lot because usually most of these vehicles, the HTV vehicle in SpaceX will bring some kind of interesting hardware, and then we get to do EVAs and install it. So it's always quite popular when you have a space vehicle that's bringing EVA hardware during your increment.
Well, why don't we give our panel a round of applause, and thank you very much. Sorry, we're going to move on. It's time to bring back up to the stage our President, Gordon England. So thank you. Oh, do we have time, Gordon? Okay.
I really think you guys can't see us over here. I know the lights are terrible. I was curious about the helium-3. Jack Schmidt, once I had some years ago the opportunity to meet with over a dinner, and I know he spoke a lot about that. And since you're talking about possibly a moon base, is anybody talking about helium-3?
Well, people are actually talking about helium-3. That's been a favorite topic of JAXA and the Japanese Space Agency. And I know that Harrison is still giving lectures on it. But until we actually get back to the moon and we look at processing regolith and so forth, that sort of is out there as a potential, but doesn't have a strategy yet to get there. It's not off the radar. Okay, so yeah, thank you very much. Thank you very much. Yeah.
So let me just wrap this up. I want to thank the panel. I want to thank Bonnie for the terrific work and your committee to put all this together. I also want to thank Mary Beth and the whole staff at TAMIS because they work very, very hard to do this. If you care to support this organization, it would be appreciated. Thank you. Mary Beth and the staff, thank you very much. And also, remember, next year, we hope to see you again. It will be in Austin in Horseshoe Bend. The topic will be brain-oriented, so a broad spectrum of the brain. It will include both the science, the engineering, and the medicine concerned with the brain. So safe travels home, and we will see you all next year, and thanks to all.